This is just a slide of some of the areas which are giving you lots of data. You may have read about the probable discovery of a Higgs boson at the Large Hadron Collider at CERN. That particular machine produces data which isn't actually analyzed in the cloud, but could in fact be analyzed very well on the cloud. It's just they set up their infrastructure before clouds came along. Anyway, that machine produces 15 petabytes of data per year. Other areas like radiology has 69 petabytes per year. If you go to future telescopes, those will be producing up to 30 exabytes of data per year. So we're living in a world which has got huge amounts of data today, and that's going up very fast. So why look at clouds? There are many reasons for this. If you go to some of the discussions, they will list some of the important features. One of the important features is a so-called elastic feature of clouds, namely you can ask for 10 nodes and then suddenly expand to 100 nodes, which is an important difference from the way one normally builds clusters. If you buy a cluster, you fix the number of nodes, lovingly write a proposal, and a year later you install your cluster. With a cloud, you can do all of that in a day or two, or an hour or two, or a second or two maybe. And so clouds have been very important in driving industry, because industry can now set up and produce and establish their computing almost instantly. The other critical feature of clouds is they are intrinsically cost effective because they're shared. You're not fixing your needs ahead of time. That's what I just described with the elasticity. So they are a very cost-effective approach to computing. So that's the economies of scale. Another interesting issue in terms of electrical power, because the clouds are by definition sitting often somewhere else, you can put them in Greenland or next to the hydroelectric power to make the cost of cooling low and the cost of power low. So they're extremely power efficient. As we'll discuss, especially tomorrow, clouds also have introduced several powerful new software models, which is sometimes called platform as a service. Whereas the core features of clouds, the actual virtual machines, is called infrastructure as a service. So here's just one example of why clouds are useful. It compares Gmail and the cost of running Gmail to various other enterprise mail systems, and you can see possibly a factor of 100 difference between a small business running an email system and Gmail with its economies of scale running your mail system. And there are many other such examples. This is one I found. Given we don't have much time, I will skip over that slide. These PowerPoints, by the way, are all available on the web. If you go to the Tumblr schedule, it points to the PowerPoints that we have available. We have the first 3 talks are already up there, and we'll put them up as we get them available. So this is this Microsoft report, and by 2015 it says there are going to be 13.8 million cloud jobs. The largest number, which the countries are the red and green things at the top, and there are 4.6 million jobs in China, which is 0.57% of the workforce. So there are a lot of, and I think our students at IU find this, that if they go to classes which involve clouds, they find that helps them get reasonably interesting job offers. So this slide here just tries to follow up a little bit on the cost effectiveness of clouds. And in some sense, clouds, if you talk to some people, Dan references in Microsoft when he talks about clouds, emphasize that clouds are basically data center technologies. how to produce the world's most efficient, powerful data center. And at the top right, we have a little table from, in fact, Microsoft, which shows, again, the cost savings from clouds. Of course, they don't save enormously necessarily from the hardware, although they, of course, buy in bulk. In the case of Google, they build their own machines. But in the cost of actually running the system, which is a large part of the cost of computing, in both networking, storage, and administration, clouds are just cheaper. If you look at the pictures on the bottom right, we have a couple of Google warehouses sitting next to the Columbia River to exploit hydroelectric power. And on the left, we have one of the standard architectures for clouds, where the unit of computing is not the server, it's the shipping container. So the person who makes the computers just makes a shipping container, and you wheel up the shipping container and plug it into your cloud center. So each shipping container has up to 1,000 servers, and in this particular Chicago data center, that has up to about 200 shipping containers. The next two slides just try to quantify the sizes of clouds. So in a report issued in 2010, a couple of years ago, says there are 30 million servers around the world total. Of those 30 million, Google had 3%, 900,000 servers. I assume they have well over 1 million servers now, maybe 1.3 million. If you look at the total power used by Google, they use 200 megawatts to run those servers. That is 1% of the total power used to run data centers, and just 0.01% of the total power used by the world. So that's actually a pretty small fraction. Clouds are not breaking our electricity budget. The largest, and the other interesting thing is if you compare Google, it has 3% of the servers, but only 1% of the power use. And that sort of illustrates that clouds are intrinsically more power efficient because Google can put their clouds in places where power is just cheaper and more environmental friendly. And if you look at the world today, maybe 20% of all the computers, all the servers, I should say, all the servers are sitting in these big commercial clouds. So that's a non-trivial amount of activity, and that sort of also is reflected in those jobs. And people who estimate the fraction of IT budget that's associated to clouds, that's again around 20%. So in 2010, that corresponds to a total of about 6 million servers sitting in clouds. So for we can compare that with high-performance computing. So there's a wonderful new machine, a Blue Gene Cube, which is being installed, or is installed, I think, at Livermore. And it has 16 petaflops. It's #1 in the top 500. And it uses 8 megawatts of power. And it is, if you look at the total performance of that machine, it is 1 or 2% of the total cloud performance. So clouds are about 100 times as powerful as the largest supercomputer. So that's an important point to realize. To build a supercomputer, you put lots of servers together. Blue Gene has 98,000 CPU chips, each with 16 cores. The Sequoia does, rather. And they're all linked together with a custom interconnect to make them have very good communication between each other. And if you look at your cloud is also a giant cluster. Actually, a similar number. The biggest clouds, individual clouds, are also around 100,000 servers, maybe going to 200,000. The key difference is that there are more clouds, but also the connection between those cloud servers is not the same high-performance, closely coupled connection that the Sequoia has. So the difference, if you like, between high-performance computing and clouds is both use huge numbers of computers because both are doing parallelism, and they're both using multi-threaded to get parallel performance. The critical difference is the supercomputers are focusing on a small subset of applications that require tightly coupled performance, and trying to persuade 1.6 million cores to run together on the same job.